Welcome to Science Bytes, a podcast from Australia's leading supercomputing and big data research facility, the National Computational Infrastructure. You'll be hearing from some of our users about their careers, their scientific research, what excites them about the work they do, and how supercomputing and data technologies help them make scientific discoveries. Coming from all around the world and from a huge range of scientific disciplines, they are the people behind the science headlines you see every day. And now, here's Andy in conversation with today's guest, Associate Professor Jenny Fisher.
Dr. Jenny Fisher is an atmospheric chemist. Jenny's an Associate Professor at the Centre for Atmospheric Chemistry and Associate Dean in the Faculty of Science, Medicine and Health at the University of Wollongong. Thanks so much for joining us today, Jenny.
Thank you, Andy.
And where do we find you today?
I'm here in Darawal country in Wollongong.
Beautiful Wollongong. Actually, years ago I spent part of my honeymoon there. It's a
Wow.
beautiful part of the world. And where did you study?
So I did my undergraduate degree in Southern California at California Institute of Technology, and then I moved to Boston for my PhD.
Fantastic. And what first got you interested in atmospheric chemistry?
Yeah, that's sort of a convoluted question for me, or a convoluted path, I guess, to the answer. So when I was a kid, my interest was really in space, and I wanted to work for NASA. I had an opportunity when I was reasonably young to go to space camp in Huntsville, Alabama, and I just got completely hooked. And I went back several times, and my mission was to understand and study space. So that's what I did for my undergrad degree. I went to Caltech and I studied planetary science, and I had some phenomenal opportunities there. I got to get involved with some research looking at dust devils on Mars, which are, as an aside, enormous on Mars because of the different gravity there and the different atmosphere. But I was doing this research, and at the same time, I was living in Pasadena, which is just outside of LA. And Pasadena is right up against the beautiful San Gabriel Mountains. But some days you would walk outside and you couldn't even see the mountains. It was that polluted and that hazy with all of the stuff that was in the air. And so I was doing this work on Mars, and I was looking at the pollution around me and thinking about how I might be able to use my science skills to maybe have more of an impact here on Earth than I was having, on the faraway planets. And so that's really kind of how I got interested in what was happening in the atmosphere, and in particular, what was causing that pollution, where it's coming from, how could we maybe change that in the future? And that's what got me into atmospheric chemistry.
Yeah, fascinating. And what brought you then to Australia and to the University of Wollongong?
Yeah, well, I have traveled the world a fair amount in my life. I really like living in different places. And when I was looking at kind of what the next steps were after my PhD, I was looking for postdocs in different places. And one of the places on my radar was Australia. I'd never been here, but my partner had and loved it. And I was looking at the community of, where is atmospheric chemistry done in Australia? Where might I be able to have a postdoc? And I had heard of the University of Wollongong because there's a really long-standing group here in atmospheric chemistry that's been around since the 90s, kind of the preeminent group for atmospheric chemistry in Australia. So had some connections, reached out, and managed to get a postdoc position here. And then came to Wollongong and fell in love with the place, and was just happy to be able to stay here and have the opportunity to pursue the rest of my career here.
Is the nature of the research in Australia different to how you would do it back in the United States?
That's a really interesting question. It's not different in terms of the way that it's done. The atmospheric science community and the atmospheric chemistry community is really globally collaborative, and we work closely with people in lots of different countries. I've always had kind of co-authors from around the world on the papers that I've written. What's maybe a little bit different is kind of the focus that my research takes, and the size of the community to some extent. And one of the things that has been quite a lot of fun for me coming here is that, on the one hand, it's challenging that we have a pretty small population of atmospheric scientists, atmospheric chemists.
Mm-hmm.
So there aren't quite as many people working on the problems here. But on the flip side, that means that I've been able to be involved in just a really broad range of different types of projects because there aren't a ton of people working on these things. And so I can get roped into things that are a little bit outside of my original area of expertise and be able to kind of go down different tangents and different routes here.
Is the data that you're collecting in Australia different from data that you would collect in the Northern Hemisphere where there's, like 3 times the population of the Southern Hemisphere or something like that? And therefore there'd be more pollution up there. There might be more data collection points, so you're getting more data. Is it different in that way in terms of the data that you're collecting?
Yeah, absolutely. And I'm not personally going out in the field and collecting the data, but I work really closely with the field scientists and the observational scientists who are going out and making those measurements. And there are a number of things that you touched on there that I think are quite important. One of them is just the difference in the number of available data points. There, vast swaths of the Southern Hemisphere are unpopulated, unoccupied, lots of large areas of ocean and desert. And so we really do have a lot less data here. And of course, there are, some socioeconomic challenges and logistical challenges in certain parts of the Southern Hemisphere as well that make that harder. What that means for me as a modeler, so I work with global models of the atmosphere. And we use these observations to validate our models to test that, I guess, what the models are predicting has some relationship to what we're actually able to observe in the true atmosphere. That data difference and that data gap means that our models are pretty well calibrated for the conditions of somewhere like North America or Europe or increasingly Asia, but less well able to reproduce what is actually happening in the atmosphere in Australia, in Southern Africa and South America, in these parts of the world. So that's a huge part of it. The other part that you touched on is kind of just the different environments that we have. And that has really big implications for atmospheric chemistry. So there are a number of differences there. Obviously, there is the much larger population in the Northern Hemisphere, and that leads to lots of emissions of things from human activity. But there are other differences as well. For example, different regulatory environments can mean that, even in some smaller populated areas, we can have different types of pollution emitted. There are climatic differences, and a lot of the natural emissions are dependent on, what are the winds like, what's the temperature like, and there are differences kind of in how the landscapes look. And so in the Sydney area, for example, one of the things that's quite interesting and quite unique is that, Sydney is this very large city, very large population in this basin that's completely surrounded by national parks and, wild vegetated areas. Now, there's lots of stuff that's coming out of the city, but there's also lots of stuff coming out of the trees. And when those things interact in the atmosphere chemically, they can make something different. And so you have these kind of diverse environments where actually what's next to each other geographically will have an impact on what you have in the atmosphere above you here.
Yeah, I suppose it would. Now, transporting back way too many years to raise in polite company, back to my 20th century honeymoon that I mentioned before in the wonderful Gong, I saw the movie Twister during that honeymoon. And it's where a meteorologist collects data by collecting these little floating sensors and putting them up into a tornado. Now, that's basically data collection in the wild, but trying to predict patterns and try to glean things, collating millions of data points of different kinds of data, monitoring things. Is that a million miles from what your goal is and what you do?
There are actually lots of really interesting ways that we get data on the atmosphere, but obviously it is a challenge, right? The atmosphere is always moving and changing, and there are differences in what's in the air right above us, like at the level that we breathe from higher up. So we actually use quite a few different types of measurement technologies. You can kind of imagine the stuff that we put a sensor out at the surface. In fact, we've even got an instrument that's on the roof of the chemistry building at the University of Wollongong here. And that's looking up at the sun and measuring the concentration of gases that are in the atmosphere between us and the top of the atmosphere. And so we have sort of some of these ground-based instruments that can give us a continuous and really precise picture of what's sort of in that whole column of atmosphere above us. But in addition to that, we also have occasionally things like aircraft campaigns where, and I've been lucky enough to be involved in a couple of different aircraft campaigns. So for those, we'll take an old passenger plane that's usually owned by NASA or NOAA or someone else, remove the interior comforts as you would, and replace them with instruments that have inlets sticking out the windows. And the benefit of that is the aircraft can actually fly up and down and make these really precise second by second measurements of what's happening in the atmosphere. So you can fly over those different environments that I talked about. You can fly, for example, through a plume of smoke from a fire that's happening upwind, and you can map out kind of some of these differences. Those are quite expensive. So, we don't tend to get aircraft campaigns all of the time, but they provide some really nice data. The other thing that's kind of been, the advance of the last 20 plus years is the use of satellite data for measuring what's in the atmosphere. And we've had a number of different satellite instruments that are dedicated to atmospheric composition and atmospheric chemistry. So what's in the air and what's happening to it. And those have, the really nice advantage that they actually cover the entire globe, in places that, like I mentioned before, are a bit hard to reach for our ground-based instruments. They come with their own challenges as well, because as you can imagine, measuring things from space has a lot of uncertainty in it. And so what we end up doing is trying to make all of these different measurements play together, as it were. And that's one of the roles for the models that I use, actually, is to try to sample the model atmosphere, so our predicted atmosphere, the same way each of these different kinds of instruments is sampling the air. And then we can get a sense of, whether they're telling us the same things, whether any differences we see are just down to the differences in the types of things that they can measure, or whether there's real differences in understanding that's coming out of these different data sets.
Speaking of data sets, they would be huge data sets, right? And you really need systems with a big amount of grunt to be able to process all that raw data and help to turn it into something meaningful that you can then begin to interpret. Which of the projects that you're working on at the moment makes the most use out of the high-performance computing and big data?
Yeah. So I guess the big data comes in two ways for me. One is through the use of satellite data. So again, as you can imagine, you've got the satellites that are kind of constantly monitoring the globe. So there's a huge amount of data there. Now, I'm not actually involved in the original processing of that data, but the use of that data does provide some pretty large global data sets for us to use. The side where I really use the high performance computing is in the modeling and in running and developing these models of what's happening in the atmosphere. You can sort of picture our models as a little bit like climate models, which I think people are increasingly familiar with. But the extra challenge that we have in dealing with the composition of the atmosphere, what's actually in the air, is all of these different chemical reactions that are constantly happening. So if you go, you look outside and it just looks clear that, there's some nitrogen and some oxygen there. There's actually a ton of other stuff that's there in really, really trace amounts, like one molecule in every million or billion or even trillion that can have this outsized impact. So all of these different things, all these different gases and different compounds, they can also react chemically with one another. And sometimes that reaction will take microseconds, and sometimes it'll take minutes or days or years. So we have these complex chemical environment. We have these various different timescales on which things are happening. And if you take all of these different things, all of those reactions are kind of happening in different ways. So you might have reaction A that creates one gas, but that gas is going to react with some other things, and everything's coupled together. And so for us, that's where the computational challenge comes in solving all of these equations for all of these different parts of the world. And so the projects that I do running these models, we really use that high performance computing to be able to push through the amount of chemistry that we can represent, as well as the timescales and resolution. So how finely can we represent a given region? And that's where the advance has really come in over the last, decade or so, is going from only really being able to represent really broad areas. So maybe several hundred kilometers in scale would all be treated the same. And you can imagine what that looks like when you're dealing with all these different environments, to pushing that resolution down now for the models that I use to the kind of tens of kilometers scale.
So that's kind of how maybe a coastal environment and a mountain environment close together, they would have been treated as one climate area before. But then, you've obviously got very different conditions uphill than what you do at sea level. So you don't really want that to be the same.
That's right. And, there are some models that are even finer than what I work with that can get down to really that kind of resolution that you're talking about. We're not entirely there for the work that I do, but it has been, that's been a real challenge, I guess, of working in the Wollongong area. Because for anyone who's kind of not familiar with the geography here, we're a very narrow coastal plain up against the escarpment, which is full of trees. We've got the city of Wollongong and the emissions there right up against the ocean. And then we sometimes get the recirculating air down from Sydney as well. So we sometimes get a Sydney pollution plume. So the more we kind of push to these finer resolutions and being able to represent these different landscapes together, the closer we can kind of get to representing what's really happening in the atmosphere. Like I said, we're not fully there yet, but we have moved from being able to represent these, I guess if you think about what those coarser models would have been, that wouldn't have just been, Wollongong together. That would have been Wollongong with Sydney, with Orange, all the way out into the kind of Western New South Wales. You've got agriculture, you've got the coast, you've got the forests. And so now we're really pushing down to being able to kind of have each of these areas at least be treated more independently, uniquely.
Yeah. No, it's a great example of what you were talking about with Wollongong, because I remember as a kid driving down Macquarie Pass, and Macquarie Pass is this big mountainous back and forth switching road, and you're going down down the escarpment, and then it's a very dramatic entry to this beautiful coastal environment having come from the hills. It's spectacular. But it is not all one environment. And so, as you say, you've got in the sky, you've got all these chemicals interacting. You're not only measuring what is happening, but getting computers to simulate what's going to happen tomorrow. That's all pretty amazing, and nowhere near something that you could do on a regular PC or Mac, I'm guessing. Is there much of a room for smaller systems to still have purpose in your day-to-day work?
Yeah, that's a good question. There are some, if you go back to some of those coarser resolutions that I mentioned, which we still do use for some purposes, you can get away with some of that for kind of global scale problems. So if you think about some of the things that are in the atmosphere that are a little bit less reactive, so they're not really operating on the timescales of seconds or hours, but more like years. You don't need to include quite as much complex chemistry there because they won't really change that much over the timescales that you're interested in. So some of those problems can be modeled, I guess, at that kind of smaller computational cost. But kind of the more we push into the advanced chemistry and then the sort of polluted environments, the more we end up needing those high performance systems.
Moving back to the big systems, which of the NCI systems do you use?
Yeah, I use the Gardaí supercomputer.
Yep, and is the software that you use, is that something custom programmed? What are you using there?
Yeah. So I use a model that's called GeoSChem, and the base of that model is written in Fortran, which is, a long-standing computer language. The model itself is, tens of thousands, hundreds of thousands of lines of code, and it's been developed by a number of researchers over several decades. Now, one of the beautiful things about this model is that it's completely open source. It's completely managed and distributed and supported by its user community. And so it actually develops quite quickly because there are about 100 research groups around the world that are currently using and developing the model. And so you can imagine we each got kind of our own individual interests in kind of some of these more specific problems or specific parts of the world. And a lot of what we do is running the model to make that prediction of what we think the atmosphere looks like, comparing that to what we see in the observations so we can figure out, are we representing the real atmosphere?
Mm-hmm.
And if not, trying to figure out why. And usually in that process of trying to figure out why, you learn something and change the model, improve the model to get a better representation of the atmosphere. Now, the beauty of this open source model and this sort of researcher community is that once you make those changes and those improvements, that actually feeds back into the publicly available version of the model. So anyone could go and download the model tomorrow, and it would have kind of all of what we as a community think we understand. And then you could come back in 6 months or a year and get an even better version that would do a better job of representing the true atmosphere.
That's brilliant. So you were saying before that in the last 10 years, the systems have evolved quite a lot. And now it's even evolving month by month as more user contributors advance the systems that you're working on or advance the software that you're working with.
Yeah, that's right. The community continues to grow. And, it's been a really supportive and open community. We have a users meeting every couple of years where everybody talks about the newest advances. And we really try to work together as a community with a steering committee to make sure we're prioritizing getting those advances into the model. There are grant-funded support teams that make sure that all of that is done in kind of the most appropriate way, and people with software development expertise putting those things in. So yeah, it's a model that, really, and I don't mean the model itself, I mean a model of working that has really, I think, led to quite a lot of advances because it's so open and just can develop so quickly.
Very cool. And what are you looking forward to being able to do in the future as high-performance computing continues to advance and the software continues to advance?
Yeah, well, kind of the current frontier is being able to do these increasingly high-resolution simulations at the global scale. So in the past, with more limited computational resource, we could sometimes push down to these finer scales, but usually we'd have to limit where we were doing that. So you didn't have the computational power to do that for the entire planet. You'd be looking at, a local area or a continental area. You might look at North America or Australia and be able to simulate that, but the rest of the globe would be at that, much coarser resolution. Some of the things we're able to do now with that higher performance are to push that fine resolution globally, and also to be able to solve the chemistry more explicitly. So one of the kind of trade-offs we always have to make is how much of the chemistry can you actually solve? And we end up kind of lumping things together and saying, oh, this will probably be good enough. But as you improve that computational capacity, then you can involve much more of that explicit chemistry, which can be quite important in regions where there's a lot of emission. So in urban areas or in areas that are at that urban vegetation interface, for example.
Yeah, like the exterior of Sydney with the national parks,
That's
like you were saying before.
There.
Yeah. So what is it that you love most about your work, Jenny?
That's such a good question. I think one part of it is the community and just being in such an open community where everybody is not just the people working on the model that work together. It's the experimentalists. It's the people who are in the labs making the fundamental measurements that go into our models in the first place. Everybody is really trying to solve these same problems and working together to do that. So that's a really fun part of it. I think the other part is just doing something, if I go back to kind of my history and coming from the space side and the Mars side, really doing something that feels quite tangible, that, we can understand why we care about what's in the atmosphere. It affects what people breathe. It affects our climate. It kind of affects everything that our entire existence, really. And so I think working on problems that are related to those bigger picture issues is really motivating.
Yeah, brilliant. Well, Dr. Jenny Fisher, thank you so much for your time today. It's been an absolute pleasure.
Thank you.
And a big thanks to you for listening to Science Bytes. You can keep up with Dr. Jenny Fisher on Twitter at @MossJennyF. NCI is on Twitter too at NCI News and on LinkedIn at National Computational Infrastructure. Bye for now.